Sea level is rising. This is in large part due to the melting of the Antarctic and Greenland ice sheets. Sea level is projected to rise 1 meter by the year 2100. And this is according to the IPCC, or the Intergovernmental Panel on Climate Change. Now, what does this mean for us? Here in the United States, 1 meter, 3 feet, what's that going to do? Well, here in the United States and other first world countries, this essentially means that we'll spend billions of dollars in preparing and building up infrastructure to protect our coastlines. Much more importantly, however, the IPCC in their latest assessment report stated that for certain low-lying coasts and islands across the ocean, sea level rise is an existential threat. Take the Maldives as an example, a group of islands off of the coast of India, whose average elevation is 1.5 meters. The IPCC projects that by the year 2100, up to 80% of the Maldives could be underwater. People will have to leave, they'll lose their homes in the Maldives and in many other islands across the ocean. So it's paramount that we understand not only that sea level is rising, but by how much. So how do we do that? Where do we get this 1 meter projection? And the answer in part is using ice sheet models. Ice sheet models are trying to understand how the ice sheets are going to evolve, and thus how they're going to project into sea level. They're typically developed by large government institutions or universities. In the US, for example, we have several from NASA and the Department of Energy, NCAR. And what they do is they take into account things like ocean dynamics and atmospheric physics and many other things. So as you might expect, they're complex. They require supercomputers to run. Single projections up to the year 2100 could take a long time to produce. And on top of that, the number of people that have access to these models is limited. My research is at the intersection of climate science and computer science. I'm creating AI-based models called emulators that are approximating the same relationships that the ice sheet models are approximating, but in a much more compact and efficient way. To demonstrate this, anybody in the audience with access to a laptop could download this model within 15 minutes. And projections up to the year 2100 can be made in under 7. This is a major contribution because now that the ability to make projections is easier, we can try new things. We can try new settings, new scenarios. We can look at how certain climate initiatives will affect sea level. Take, for example, imagine I was a researcher that was interested only in trying to approximate how air temperature is going to affect sea level. I can make minor changes to air temperature and see how they affect outputs, and I could produce those results, run those experiments in a matter of minutes rather than weeks or months. So my day-to-day research is coding the Bayesian recurrent neural network architectures that we use, creating the training procedures, and curating the data sets. My current direction is now to look at the models themselves and delve into them. By using explainable AI tools, we can learn and extract insights about the physical world from the way that the models are learning. In conclusion, my research is enabling experimentation. Because we can produce projections quickly, we can try new things. We can try new variables. We can try different settings, and this will inform our understanding of sea level. My research is additionally democratizing sea level science. Because anybody here can download it and have it on their laptop, more people can get involved, and more people can learn and run experiments and contribute to our understanding of the reasons behind our sea level rise problem. This will drive innovative solutions and help us come up with answers to questions that we've had for decades. And in turn, this will drive societal change and helping us to prepare for future sea level rise. Thank you.